So, like Dr. Wynn said, my name is Eckman, and we looked at cannabinoid polymer interactions presenting evidence of PCTT leaching in hemp vapes. Alright, so taking a look at the common types of cannabis vapes, we see three main vapes used in the industry. The traditional 510 threaded cartridge is the most common. We also have the pod vape down below it here on the left, which saw a little bit of popularity. And then lately we see a lot of these disposable vapes, also called all-in-one vapes. The name's kind of moving away from disposable because the lithium-ion batteries in here are really not disposable. But essentially, despite the types of vapes, they all kind of act the same way. You've got a reservoir that's going to hold your cannabis oil. You've got a heating element and a wick to absorb the cannabis oil. You'll have a mouthpiece and a vapor pad that connects the heating element to the mouthpiece, actually delivering the vapor to the consumer. Taking a look at what these vape carts are made out of, we traditionally see a couple different materials used in here. For the tanks, which was really the main focus of our research, we mainly see borosilicate glass, but commonly also will encounter some polymers. Back earlier in the industry days, we saw a lot of ABS and polycarbonate use, as well as polyesters such as PETG, but the industry has since moved away from those to other polyester-based materials such as PCTG, PCTT, or actual like patented proprietary blends such as this Tritan. And then the wick material, as we kind of see in here on this diagram, is generally lower in the cartridge. It's a porous ceramic. I don't know what happened with the formatting on the slide here with those, but I was just touching on a couple different elements that we normally see when it comes to metals in the coil. Really, the ones to note there would be bismuth is a lead solder replacement, but despite that, we still sometimes do encounter lead in these vape carts. So sorry about that. I think we got it figured out now. Getting back into this, looking at the various polymers that we utilize in vape cartridges, we see a couple of main ones, and they're all really copolyester thermoplastics, and they're all created by taking this diacid, which is a terephthalate, and reacting it with various diols. So we have ethylene glycol, cyclohexane methanol, and then this tetramethyl cyclobutane diol. The choice of the monomer, which are these guys down here, is going to play a role in the polymers and properties, whether it be using a ethylene glycol, which is a more flexible molecular structure, allows for a little bit better chain stacking and more rigidity, or using something like a really bulky group could potentially add more intermolecular forces, electronic interactions, and help improve either heat resistance or chemical resistance. One thing that's really interesting to note here that I didn't realize before getting into the polymer chemistry side of things is if we see here PETG, which is polyethylene terephthalate glycol modified, and PCTG, which is polycyclohexylene dimethylene terephthalate, they really are made up of the same molecular backbone, essentially, of monomers, but they're named differently depending on the percentage of the monomer makeup. So if you have more of the ethylene glycol, over 51% in molecular ratio compared to the CHDM, it's going to be a PETG, which is commonly seen in like plastic water bottles. If you have more of the CHDM, which is that cyclohexane dimethanol monomer, it's going to be labeled as a PCTG. So getting into now what these really look like on a molecular backbone, we see down here on the bottom left, that's the structure of both PETG and PCTG, like I was kind of saying there. But if you have more of that EG subunit on the left, which is the ethylene glycol, we call it that PETG. If you have more of the CHDM subunit, it's a PCTG. Now Now, why that's important is early vapes utilized PETG, but the industry quickly saw potential cracking and chemical resistance issues with terpenes degrading the PETG. That caused them to shift to PCTG a handful of years ago, and more recently we're starting to see, in about the last 6 months to a year, hardware manufacturers switching over to this PCTT blend, which we see down here on the bottom right. This polymer utilizes that bulkier ring structure of the CHDM monomer and combines it with the really bulky tetramethyl cyclobutane monomer that we saw on that last slide. And that's going to, again, further enhance the chemical and heat resistance based on the intermolecular forces and electronic interactions going on in that ring structure. It adds some bulk to it as well. That helps prevent some of the crystalline polymer structure from forming. It creates more of an amorphous polymer. So our original research design was, we really intended to look for heavy metals and develop a method for quantifying heavy metals in vapes based off of some research that we saw that was recently published that inferred that there could be some reproducibility issues when it comes to utilizing the currently accepted methods for heavy metal analysis in vapes at the state level, and that was using ICP-MS methods. We figured that our proposed method might be a little bit better through using SEM-EDS, that's scanning electron microscopy, coupled with an electron detector sensor. What we were originally going to do was just dissolve the vape contents in some hexane, pass it through a nitrocellulose filter. That filter would catch any metal particles, which we could then image and quantify under the SEM, and then further use particle analysis software to really count and see how much metals we were reaching. But as we see here by this photo, we had a lot of precipitate crashing out of the hexane solution. This was something I found interesting because my time in the industry before this, I had dissolved plenty of vape cards and never ran into anything like this before. And that unknown precipitate was actually volatilizing under the electron beam inside the SEM, causing all sorts of issues with our analysis. So we had to kind of take a stop and refocus our research game. And that's kind of what the contents of this presentation is on today, is really, well, what is this that we are extracting or reaching into our cannabis oil, and how much is actually coming out? The early hypothesis was it was potential polymer leaching from the vape cart reservoir. So in order to isolate it, what we did was first obtain the mass of the vape when it was full, and then emptied it using gravity. We didn't want to introduce any heat or solvents that could potentially further cause degradation or leaching. So these were just left to sit upside down for 24 hours, and probably about 95% of all the distillate just dropped out with gravity. We then dissolved the oil in hexane and used vortex agitation to actually cause the precipitant to crash out of solution. From there, it was centrifuged into a pellet, and we decanted the solvent, repeated that process twice, effectively washing the polymer, removing any cannabinoids or terpenes that could cause potential issues, mainly for in the SEM, because it's pretty sensitive to volatiles. From there, we started the gravimetric analysis to really tell us how much we extracted or obtained from the vape samples. This was done by obtaining the mass of a dried nitrocellulose filter in a desiccant chamber for a day. That just removed any moisture from the filter. We used hexane to transfer the pellet out of the centrifuge tube, and essentially through a Buchner funnel setup, captured that pellet and dried it, removed any of the solvent, and finally obtained the mass of the dried filter and pellet. From that, we had a sample size of 8 vapes. 7 of them had polymer containing construction. The average precipitant recovered was 4.8 milligrams, representing an average of 0.82% on a weight by weight percent basis compared to the amount of oil that we originally started with. We can see here on the bottom though that the maximum amount of precipitant recovered was 9.7 milligrams, which represented 1.5% weight of the actual oil. and that wasn't even the worst offender. When we look at the worst weight by weight percent basis, we saw that vape number 5 had actually 1.61% of the actual distillate oil weight was this unknown precipitate, and that was 9.1 milligrams. So after we isolated, we wanted to take a look at what it looked like under the microscopes. Up on the top, we'll just briefly cover this because it didn't really give us a lot of information on the polymer. But we took bright field and dark field microscopy photos, as well as just a standard stereoscope photo, and we saw that the structure was roughly amorphous and not supercrystalline. Using the SEM on the bottom, we utilized 3 of the different modes of the SEM. In the far left image, we see the backscatter electron detector, and the SEM was set to topographic mode. So here we're just looking at surface morphology and characteristics of the polymer itself. The second photo used composition mode, and composition mode features atomic level contrast brightness, meaning that heavier elements are going to show up brighter, and that's what we see with that one little white speck in the middle. Point analysis on that actually showed it to be an aluminum particle. And then finally here, using the secondary electron detector, we were able to get really good morphological photos that was really closely zoomed in on the crack, and that photo is slightly rotated just because the stub rotated in the SEM. Moving on to analyzing the physical properties, this is where we start really getting into the characterization of our unknown. We did a quick melting point. It's not an ideal test to do on polymers. Ideally, we would do a TGA, thermogravimetric analysis, to really analyze the glass transition temperature of these polymers, but we made do with what we had here, and we saw that we had a pretty broad melting range, which is pretty indicative of a copolymer, and although didn't really narrow it down too much. Moving on to the solubility testing, we wanted to see what it would dissolve in, and it would only dissolve in chloroform, which was actually nice because we needed it to dissolve in that for spectroscopic analysis. And that also kind of gave us clues to copolyester polymers based on that solubility parameters. Moving into the spectroscopic results, this is where we really got some good information on what we were precipitating out. This here is a photo of our spectra from ATR FTIR, and FTIR shows the functional groups present in the molecule. We identified aliphatic CH3 stretches on the far left, but really the main points of interest were the carbonyl stretches at about 1712 inverse centimeter wave number down there, as well as our various carbon-oxygen stretches that indicated that we did in fact have a polyester. We can see that there is 2 stretches right here really close together for carbonyl to oxygen stretches, representing the 2 different carbonyl to oxygen bonds right here. The shifts basically being dependent on which ring it was attached to, causing just minor electronic effects shifting it in the spectra. And then on the right, this is a library reference that we found for PCTT that correlated almost identically to the stretches and bands that we saw, and that provided us a lot of evidence that we may potentially have PCTT as a polymer of interest here. Moving on to Raman IR analysis. This was done by 2 collaborators. We had Nick Gordon, which is a student and faculty, actually is employed by the university now. He performed an initial Raman analysis on this, and then we also sent it out to Dr. Vernon Malone, who actually created this graph that we see here, the spectra that we see here. He did a baseline corrected normalized Raman spectra of both samples we sent out of the precipitate that we recovered, but also scrape samples from the exterior of the vape cartridges. And as we can see here, it really closely lines up. We did identify 3 unique peaks, which are still unidentified. We believe it could be potentially contamination on the outside of the vape or degradation. But ultimately, we used carbon NMR and really a whole suite of NMR analysis to really prove that what we have is what we think we have. So we did a carbon NMR, hydrogen NMR, HSQC, and COSY, actually performed by Dr. Mosey and then analyzed by myself and then Jackson here. I just decided to really quickly throw up the carbon NMR here with the individual carbons labeled corresponding to the peaks that we saw. But really all of our evidence came in the form of this table right here. What we see is both the proton and carbon NMR for our spectra, and then a spectra that we found in published literature that actually used PCTT mixed with various degradation products, and those were ethylene glycol and then isophthalic acid, which is that IPA. Ethylene glycol present as a breakdown process and synthesis reaction, and then the authors of the other study used that IPA as just a modifier in 3D printing filament. But what's really important here is we can see that the highlighted cells, those show that we don't actually have any of the IPA or the ethylene glycol inside of our spectra, meaning that we most likely have a neat, pure version of PCTT, not adulterated with IPA or contaminated with ethylene glycol. If we get to looking at the structures here, this bottom structure is kind of referencing that study that I was talking about with that ethylene glycol and IPA unit inside the molecular backbone structure. On top is what we came with the over corresponding assignment for carbon NMR. But through really combining the melting point, solubility, FTIR, Raman, and host of NMR analysis that we did, we were able to pretty definitively determine that we have some PCTT leaching in cannabis vape carts. Suggesting a plausible cause for this. More testing is going to be done to really see what could be driving this, but it is a pretty significant finding with implications for the industry. We believe that it could be potentially either terpenes or contact time, or also even both, and that's where kind of that future testing comes in. We know that terpenes can act as a solvent. Here we see terpenes being compared to hexane with their Hansen solubility parameters, which is basically showing that these terpenes can act very similar to the solvent hexane. And then another thing was contact time was noted as a key driver for leaching, with all of our samples starting to leach after about a year of sitting in the vape cart, and that was through reference batch sample data. So we'd certainly be interested in doing future shelf life testing and terpene concentration studies to see what variables may play a role when it comes to polymer leaching, but also to see if any of these polymers actually aerosolize and enter the vapor stream, because we know that they may be entering the vape cart, but we don't know if they actually are exiting and being inhaled. And then finally, just like to quickly acknowledge Dr. Derek Wright, Dr. Vernon Malone, Nicholas Gordon, Dr. Adam Mosey, and Jackson Run for assistance with this research. And on top of that, all of the SEM imaging was done through a grant made possible by the NSF, so we would like to acknowledge them as well. Is there any questions? Yes.
Question. So you said these were all CBD vapes, correct?
Yep, so it was all hemp-derived vapes. There was one that was an HHC vape obtained from a local smoke shop, but they were all either hemp-derived or product of the hemp bill.
Okay, so the one thing that I was wondering is, because I know that CBD is a solid, it's may also be dissolved, and you did mention possible terpenes. Was there any analysis you guys did to try to figure out what the carrier oil was, if it was a terpene, or if it was, say, some other type of oil that's dissolved in it?
No, that was something that I wanted to do, but we ran out of time, unfortunately. We wanted to also do a GCMS analysis of the actual terpenes. One, to see if the terpene percentage was what the initial testing lab claimed or manufacturer claimed, but also to really try and identify if there's a specific terpene or terpene concentration that is really impactful or important for leaching, but unfortunately we just didn't have enough time.
Yeah, if somebody picks up on this project, you could really rapidly just by NMR be able to tell what the major other component was in
Yep.
CVDs.
Off the top of my head, I know propylene glycol or PEG 400 are the common carrier agents, with propylene glycol by far being the most common. Yes.
Did you try DMSO?
We did. So according to what we found on different literature, it was really only soluble in chloroform, deuterated chloroform, and then THF, if I recall correctly. We also tried a whole host of solvents to make sure that they were compatible with the filter, and that presented a lot of issues too, where there was potential to dissolve the filter. So we wanted to be cognizant of that as well, so that we could actually capture the pellet.
So you said it was like 1.68%. What was that, PEG?
So, our maximum weight by weight percent, Carter, is that what you're mentioning?
Yeah.
Yes.
That's a lot. So like, how old are these vapes that you're testing? I know you said like future, you're gonna look into shelf life and everything, but do you know like how old these ones were?
I don't have the exact dates off the top of my head. I want to say that the oldest one was right around 2 years at the absolute oldest date, and the newest one was right around 3 months. We did try to plot out to see if there was a linear or exponential relationship between leaching, but we just didn't have enough data points to get a really accurate representation. If we had enough time, I probably would have liked to run 20, 25 samples, but again, cost becomes a factor then too.
With the one vape that didn't have the polymer construction reservoir, what was the result of that?
So that one didn't see any actual coming out of it, and that's why it was omitted from the average there. It was basically just taking a look at the polymers then, but we really wanted to take a look to see if any glass or silica, that type of stuff, leaches, and had we had enough time, we would have placed that filter under the SEM to really get a good look at it. But just based on the gravimetric analysis, there was no change in mass on that filter down to the 0.1 milligram. So we just omitted that data.
So for future safety standards, would you recommend moving away from polymer construction?
I think it's a little too early to tell. Additional research would probably have to be done, because when we were originally designing that study, not all of the samples caused SEM issues with these polymers crashing out, but we did have early preliminary data that there was silicates coming out of these vapes that would potentially cause silicosis, and then just a vast amount of metals coming out too. So I think future research would have to be done on that to definitively tell.
Okay, thank you.